Hello everyone, this is Professor Pawan Shavankar and I welcome you in a 47th lecture of Control System Engineering, and today we will discuss one more numerical on Bode plot. So in this numerical we can see here a quadratic pole present, s square plus 5s plus 120. So whenever quadratic pole is present in numerical, how to solve it, let us discuss. So our g of s h of s is 242 s plus 5 by s plus 1 s square plus 5s plus 121. Our very first step is to convert our numerical in a standard form, that is a 1 plus s form. So g of s into h of s equal to 242 as it is. Then we will take out 5 as a common, so 5 into 242 in bracket what remain 1 plus s by 5 divided by s, then s plus 1 can be written as 1 plus s, no issue. And quadratic pole, here we want again 1 plus s form, so we will take out 121 as a common, so 1 plus something of s plus s square by that term. So here 121 is taken as a common, and what remain here 1 plus 5 by 121, so 5 by 121 into s plus s square by 121. So we have converted our whole g of s h of s term in 1 plus s form. So calculation 5 into 242 by 121, so 121 into 2 becomes 242. So 121 2s are 242 into 5, so in numerator 10 1 plus s by 5 divide by s 1 plus s, and in another bracket 1 plus, if you solve this on calci 5 by 121 you will get 0.041, so 0.041 s plus s square by 121. So this is our converted standard form. Now let us calculate the corner frequencies to arrange all the terms in for magnitude plot. So which term will come first? So obviously this is a k, this is a first term, and pole at origin will be the second term. Among these simple zero, simple pole and quadratic pole, which term will come first, that we will check here. So corner frequency, so if we take this simple 0, 1 plus s by 5, so compare it with 1 plus ts. So t will be, so t is a coefficient of s, here coefficient of s is 1 by 5, hence t is equal to 1 by 5, and corner frequency omega c equal to 1 by t is equal to 5, so 5 radian per second. Second, this term simple 0, so 1 plus s, again compare it with 1 plus ts. For this t is equal to 1 as well as omega c is equal to 1 by t, so 1 by 1 is 1 radian per second. Now what about quadratic pole? We can't compare this quadratic equation with a simple 1 plus ts. So we have seen in a time response analysis that in transient state this equation has a very standard form, that is s square plus twice zeta omega n s plus omega n square. So this is standard form for auxiliary characteristic equation. So s square plus twice zeta omega n s plus omega n square should be compared with this term 1 plus 0.41 s plus s square by 121, or simply before we convert it into standard form we have a simple quadratic equation s square plus 5s plus 121. So instead of taking this for calculation, consider this equation. So s square plus twice zeta omega n s plus omega n square equal to s square plus 5s plus 121. So here omega is nothing but frequency called as a corner frequency. So omega c or omega n has the same meaning, corner frequency. So omega n is under root of 121 because omega n square is 121. So we will get here 11 radian per second. Okay, so corner frequencies of all the parameters available in a question has been solved. So corner frequency for this is 5, for this is 1, and for this is 11. So what will be the sequence? Sequence is simple pole because corner frequency is 1, then secondly 5, and lastly 11. Okay, now one more important term. Whenever quadratic pole is present in a numerical, either quadratic pole or quadratic zero, whenever any quadratic pole or quadratic zero is present in a numerical, we have to calculate correction value. And correction value is nothing but a a peak like this. So suppose this is a graph for particular magnitude. So whenever if you're talking about a quadratic pole or quadratic zero, in this graph there will be this structure. Okay, this peak value comes. So and it has a certain value measured in a decibel. So this peak can be calculated, or correction value can be calculated as correction value is 20 log twice zeta. Okay, 20 log twice zeta, and formula is minus 20 log twice zeta. So before we go for this formula, let us calculate zeta. From here, twice zeta omega and s should be compared with the 5s, hence twice zeta omega n equal to 5, hence zeta is equal to 5 by 2 into omega n, so 2 into 11, and this value is zeta is 0.22. okay, zeta is 0.22. So correction value is minus 20 log twice zeta. Zeta is 0.22. So correction value in decibel is plus 7.13. if you calculate it, 7.13 and decibel dB. Correction value is nothing but that speed breaker you can see on a road, speed breaker. So suppose this is a graph, plane graph, and suddenly one peak comes in that way, that is known as a correction value, and it has certain value of decibel. Okay, so from datum line, how much above on the datum line it can be measured in decibel. Okay, so that we have calculated as a 7.13 decibel. So the next is magnitude table. So parameter, then magnitude, or individual magnitude, we can say individual magnitude, then cumulative magnitude, then range and slope. So very first parameter is k. K is resultant gain of system, that constant value comes out. So from in standard part, constant is 10, then pole at origin, then simple pole, then simple zero, and then quadratic pole. How we arrange this sequence? At very first number k should be written, then either simple pole or simple zero on second number. Then according to corner frequency we arrange the sequence. So simple pole has a corner frequency 1, simple 0 has corner frequency 5 and quadratic pole has frequency 11. So 1, 5, 11, third, fourth and fifth. So parameter k equal to 10, individual magnitude 20 log 10, 20 log 10 is equal to 20 decibel. Cumulative magnitude is same, 20 decibel. No range and slope is straight line. Second parameter is pole at origin. So 1 by s, magnitude is minus 20 dB per decade. We already discussed the individual magnitudes of different parameters. Pole 0, quadratic pole, quadratic 0, pole at origin, 0 at origin. So if it is a pole, minus 20. Then simple pole 1 by 1 plus s has magnitude minus 20 again, minus 20 dB per decade. Then at third number, simple 0, so 1 plus s by 5, and it should have magnitude. If it is a 0, so magnitude will be plus, so plus 20 dB per decade. And lastly, quadratic pole, so 1 by 1 plus 0.041 s plus s square by 121, and it has a magnitude. If it is a pole, so it is a magnitude minus quadratic, that's why 40 decibel per decade. Okay, now cumulative magnitude will be first term write down as it is, minus 20 dB per decade, this term, and add in this fashion like this. So minus 20 minus 40 dB per decade, minus 40 plus 20 minus 20 dB per decade, and minus 20 minus 40 minus 60 dB per decade. Got it? So minus 20, minus 40, minus 20 and minus 60. What about the range? For range we need a corner frequency. We never calculate corner frequency for k and pole at origin, 0 at origin. Here corner frequency omega is 1. Here corner frequency omega is equal to 5, and here corner frequency omega is equal to 11. So corner frequency always start from 0 or very first number, that is a 0.1. Our graph is started from 0.1. So 0.1 to next is 1. So 0.1 to 1. Then next to again next. So 1 to next is 5. 1 to 5. Then 5 to next number is 11. And from 11 to next is not present, so infinity. Okay. You should go like next number. So 0.1 to 1, 1 to 5, 5 to 11, 11 to infinity. And slope will be cumulative magnitude according to cumulative magnitude. So slope is along minus 20, along minus 40, along minus 20 and along minus 60. So minus 20, minus 40, minus 20 and minus 60. Okay. So this is a magnitude table. Now next part is phase plot or phase table. For phase plot we need to calculate the formula for angle. So suppose your pole is 1 plus s. This is for just example. Okay, so suppose pole is 1 plus s, replace your s by j omega. So your pole will be 1 plus j omega, and formula is tan inverse imaginary part by real part. So formula is tan inverse, imaginary part is coefficient of j, so imaginary part is omega, real part is 1, like that. If it is pole, formula will be minus. If it is 0, formula will be plus. So for 1 plus s, as it is a pole, so formula is minus tan inverse omega. Then again we have 1 plus s by 5, so it can be written as 1 plus j omega by 5, and formula is tan inverse but positive because it is 0. So tan inverse imaginary part is coefficient of j, so coefficient of j is omega by 5. Okay, omega by 5 divided by 1, so that's it, plus tan inverse omega by 5. Now what about quadratic pole? So quadratic pole is 1 plus 0.041 s plus s square by 121. So replace with j omega. 1 plus 0.041 j omega plus s square, so j square omega square by 121. Now what is j? J is under root minus 1, so j square will be minus 1. So if we put j square is equal to minus 1, so this bracket will be 1 plus 0.041 j omega minus omega square by 121. Got it? Now we will apply formula. This is pole, that's why formula is minus tan inverse. So tan inverse imaginary part is coefficient of j, so coefficient of j is 0.041 omega, this much part only, so 0.041 omega divided by real part is 1 as well as minus omega square by 121. So real part is 1 minus omega square by omega square by 121. So this is a formula. Okay, so phase plot, let us make a table. First is omega, then 1 by s, then 1 by 1 plus s, then 1 plus s by 5. Quadratic pole, 1 plus 0.041 s plus s square by 121, and then total. Before we consider different values for omega, here formula is minus tan inverse omega, here plus tan inverse omega by 5, here formula is minus tan inverse 0.041 omega by 1 minus omega square by 121, and then total. Okay, so this is our table. Now at random you can select the values of omega, different values of omega. So suppose I choose 0.1, 1, then 5, 8, 10, 20 and so on, like up to infinity, or 100, 200, whatever. So for all these values of omega, here angle will be minus 90 because pole at origin, so angle is decided. So for every value of omega, angle will be minus 90. Done. And here put omega is equal to 0.1 to up to 20 and calculate all the values with the formula minus tan inverse omega. So what we will get 1 plus, sorry, all the values will be minus, so minus 1.14 minus 1.13 minus 45. For omega is equal to 8 will get 58 minus let us check one value with the calci. Let me check it. So minus tan inverse minus shift tan inverse of 0.1, value is minus 5.71. Okay, just a minute. So here we will get minus 5.7, then minus 45, minus 78.6, minus 82.8, minus 84.2, then minus 87 point something, minus 90 approximate. Further after 20 it will close to 90. Okay, for any value like 100, 200, 1000 will get more than less than 90 degree. Okay, then for plus tan inverse omega by 5 we will get plus 1.14 plus 1.13 plus 45, then 58, here 63.4, 75 and 90, plus 90. Okay, plus all the values are plus. And for this big bracket value will be for 0.1 it will be minus 0.23, minus 2.36, minus 14.4, minus 34.8, minus 67, minus and for omega is equal to 20, suddenly value is plus 19.5, plus 19.5. Whole column is a value with a minus sign, but suddenly for any particular value is minus 19.5. So it is not possible to jump with a plus value because minus 90, minus 120, minus 150, minus 180, minus 210, minus 230, minus 250, minus 280, our graph is going down. Okay, but suddenly if any value comes plus, so it is quite difficult to jump to the certain value. So what should we do? If it is a quadratic pole, minus sign, quadratic pole, so you should subtract or you should take minus 180, like 19.5 minus 180, so you will get a minus value. Okay, if it is a simple pole and all value are the minus, suddenly if any value you get as a plus, so you should do 19.5 plus minus 90 if it is a pole. If it is 0, so plus 90. If it is a quadratic 0, plus 180. So as this is a quadratic pole, so you should subtract this value from 180. So 19.5 minus 180. Why we done this? Because suddenly we got this value plus. So 19.5 minus 180 is minus 160.4. 160.4. And lastly minus 180. So total angle like minus 94.7, minus 126, minus 138, minus 149, minus 177, minus 261 and minus 270. Okay, so we have completed our phase plot. Now let us draw Bode plot. So already we have taken reference point at omega is equal to 1. This is our 1, so this is our point 1, and the reference magnitude lines like minus 20, minus 40, minus 60 and minus 80. So this is a reference point, should be marked at 0 line. This is a 0 line, then minus 20, minus 40, minus 60 and minus 80, and at omega is equal to 1, this intersection point known as a reference line. Now very first graph for k is 6. For k is equal to 10, we got 20 dB. 20 log 10 is 20 dB, and the graph is straight line. So at 20 dB draw horizontal line. This is 20. Okay, a question may arise in your mind like this is a minus 20 and we got plus 20 for k. So what does it mean minus 20 minus 40 graph? If your lines above to below comes above to below, that means it is in a negative. Obviously all the portion above the 0 line is plus and below is minus. So this minus 20 graph comes from above the datum line to the below the datum line. So this is a minus. Okay, but for k is equal to 10, graph is 20, so it should be drawn with a thick plain line. Line should be straight. Use scale and all graphical instruments. And this graph is 20 log 10 is equal to how much? 20 dB decibel. So first graph is completed. Next is minus 20, then minus 40, minus 20 and minus 60. Okay, and range is 1 to 0.1 to 1, 1 to 5, 5 to 11, 11 to infinity. Remain the sequence minus 20, minus 40, minus 20, minus 60. Minus 20 from 0.1 to 1. So this is the first graph. Okay. Now if you have particular value of k and you got graph for k, so shift your graph by that amount. So shift this blue line from here to here. Okay, so right now I'm changing the ink. We need to shift this graph, this blue line, from here by 20. So 20 is this point, that means this point should come at this level. So this graph should be shifted above. Parallel to that line. Both lines should be parallel. Now this graph is 20 dB per decade and minus. Okay, minus 20 dB per decade. Later on minus 40. So along 40 line you should draw the graph, and 1 to 5. So 5 point is this. This is omega is equal to 5. Okay, so this graph is for minus 40 dB per decade. Then next is minus, again minus 20. Now for minus 20 and 5 to 11, so this is 5, so this is 10, this is 20, 11 is this one up to this line, and according along minus 20. So take a parallel, place your scale parallel to 20's line and draw 20's graph, like suppose somewhat here up to 11, and from 11 to infinity. Now from 11 to infinity with along 60. Okay, 60. You can see here magnitude plot. Minus 20, minus 40, then minus 20 and minus 60. So from here along 60 line, this is a 60's line, so parallel to this, like here. And last graph is for quadratic pole, so we need to draw correction value. And what was the correction value? Correction value is 7 point something, 7.13 dB, and corner frequency was 11. So at 11 you should show correction value how much, 7 point something. Now look at this portion, this is scale of 20, this is a 20, so one block, if 5 blocks adjusted in a 20 dB, so one block has a value of 4 dB, and we need to go for 7. So suppose from this point seven, so from this 4, 8, suppose here. Okay, so at this point you should draw one slope like this. Okay, and erase this portion. And just continue, because it is going to infinity, and this is known as correction value. Okay, 7.13 dB, and this graph was for minus 60 dB per decade. So we have completed our magnitude plot. Now phase plot. So suppose minus 90, minus 120, minus 150, we are considering scale, minus 180, minus 210, minus 230, minus 270, and so on. So we have selected our omega as 0.1, then 1, suppose at this, then 5, then 10, then 20, and so on. So first value is minus 94.7, suppose here, then 126 for omega is equal to 5, sorry, at 0.1 value is 94 here, then for omega is equal to 1 value is 126, so this is 120, one block is of 6, so 126 here, then for omega is equal to 5 it is 138, omega is equal to 5, this is 150, 144, 144 and 158, suppose. Suppose here 138, then 149 for whom is equal to 10, sorry 8, for 8 we have considered on this line. 150, 149 suppose, somewhat here, slightly above the 150 line. Then 177 for 10, 177, this is 180, this is 180, so 180, 174, 177 here. And 216 for 20, 216 for 20, 210, 230, 270, suppose here, and 270 for omega is equal to infinity. Okay, suppose here somewhat, this is for infinity actually, so no need to check that point. So graph will be smooth curve through these all points. Okay, so this is phase plot. Now GM and PM, gain margin and phase margin. Now gain margin, for gain margin, this is a reference line for phase plot. So where intersection of 180 line and phase plot through that point go upward, and distance between 0 line and peak value will get gain margin. This is a GM, and it is below 20 suppose, because one patch is of 20, so suppose 18 dB. Okay, so 18 dB will be your GM. It may vary for your construction, because you will draw with all graphical instruments. I have drawn very simply just by pen, so value may vary. Okay, so try to draw your sketch with possible accuracy. And what about PM? Intersection of 0 line and magnitude plot, find that intersection, comes down, and the gap between 180 line and phase plot will give you PM, phase margin. So this is 30 degree, one patch is of 30 degree, then 36, 42, suppose 42, 45 degree or 44 degree. Again this value may vary. Okay, so this is a GM and PM. Got it? One more thing, omega GC and omega PC. Omega GC is frequency at gain margin. So where we got gain margin at this point, so gain margin has a frequency 10. Okay, so omega GC is 10 radian per second, and omega PC frequency at phase margin. So phase margin, where we got phase margin we got at, suppose somewhat here. So this is omega is equal to 1, this is omega is equal to 2, and omega is equal to 3. So between 2 to 3, so 2.1, 2, 3, 4, 5, 5. So 2.5 radian per second. Got it? So this is all about the Bode plot. And what about the stability? If you get gain margin below the 0 line and phase margin above the reference line, that is 180 line, your graph or your construction is stable. So system is stable. Okay, because gain margin you got below 0 line and phase margin above 0 line. Okay, so we'll stop here. Thank you.